The whole world goes wireless and digital. One technology is right in the center of these two megatrends: Software Defined Radio, or short SDR. Do you know how it works and how you can take advantage of it? Grüezi YouTubers, here is the guy with the Swiss accent, with a new episode and fresh ideas around sensors and microcontrollers. Remember, if you subscribe, you will always sit in the first row. Software Defined Radio is a relatively new technology, and it was extremely expensive in the past. Then came this small USB dongle for $10 and changed all. And other, more capable devices like the Hack RF1 for $300 pushed this technology into mainstream. Today, most modern radios used, for example, in smartphones, in amateur radio equipment, or in satellites are SDR radios. What does it mean for us? Suddenly, we can listen to all wireless services and even build our own GSM base station if we want. Or, as you see here, you can listen to a satellite which is 36,000 kilometers away in a geostationary position.
iTunes goes not to lose in the spectrum, Gary. Microphone back to you. Zulu Sierra 6 Yankee Italy OE9 MBI.
Here I connect via internet to an SDR receiver which is located in the UK. I leave a link if you want to try it yourself. One word of warning. Please make sure your actions are legal in your country. As a rule of thumb, transmitting signals is generally forbidden unless you are licensed to do it. Listening to commercial services might also be restricted. In this video we will look on how radios worked before SDR. Maybe we can learn something useful. Look at the core of SDR, the IQ signal, and how it is created. Build a universal transmitter and a universal receiver. Look at some applications of the technology which are interesting for makers. Very important, we will keep it simple and do not go into complex numbers or any other such thing. This is why I will simplify as much as possible, but not more, exactly as Einstein proposed. We all know radios since our childhood, and we use them daily to listen to our favorite FM station, for example. But how do such radios work? Our ears only can hear frequencies below 20 kHz, and for an older man like me, even less. But the FM station we listen to is maybe on 100.7 MHz. To get this working, the carrier is modulated with a sound signal. A typical signal of such an FM station looks like this. We see a curve with a center of 100.7 MHz and two so-called sidebands which contain the sound signal. So our radio has to demodulate the music or voice from this carrier. How is this done? When FM stations were invented, 100 MHz was a very high frequency and costly to handle. This is why the engineers wanted to get to lower frequencies as soon as possible. This can be done by a mixer, which has two inputs. One for our radio signal on frequency 1 and another for a constant frequency 2 signal. At the output of the mixer, we get a signal containing two different frequencies. Frequency 1 plus frequency 2 and frequency 1 minus frequency 2. Let's do an example and assume frequency 2 is 90 MHz. Then the output frequencies of the mixer are 10.7 and 190.7 MHz. 10.7 MHz is still a high frequency, but for sure lower than 100.7 MHz. If we add a 10.7 MHz filter after the mixer with a bandwidth of 150 kHz, we only get the signal of our favorite station. All other frequencies, also 190.7 MHz, are dropped. 10.7 MHz is called intermediate frequency or IF because it is between the carrier frequency and the audible sound. And the generator of frequency 2 is called local oscillator or LO. From this example you already learn. In RF we not only need modulators and demodulators, we also need frequency generators, mixers and lots of filters. This method has another huge advantage. We can use a fixed frequency filter for 10.7 MHz. Fixed frequency filters are much simpler and cheaper to build. Why is the IF fixed? Let's assume you want to listen to the favorite of your partner on 103.7 MHz. You only change the local oscillator frequency to 93 MHz. And your intermediate frequency for your partner's favorite is at 10.7 MHz. Cool. After this IF filter we add a demodulator, an audio amplifier, a loudspeaker, and ready is our analog receiver. Let's now digitize. Usually this is a simple process. We use an analog to digital converter or ADC to create a digital signal. We even could use one of our Arduinos to create such a digital signal. If you saw Great Scots or my walkie-talkie videos, you know that this works fine with voice. To achieve this, we could connect our FM antenna to the Arduino ADC, add a sketch, and we would have a digital receiver. Simple and cheap. Unfortunately, the Arduino ADC takes at least 13 microseconds to convert one value. This means that we can only use it to digitize signals of a few kilohertz. But we need 100.7 megahertz. What to do? We could buy a much faster ADC, but prices increase exponentially with speed. And if we want to receive Wi-Fi signals at 2.4 gigahertz, we have to give up this idea quickly. But we can learn from analog radios. We also can use a mixer to reduce the frequency. For our Wi-Fi signal, we could, for example, use a local oscillator frequency of 2389.2 MHz. Then we again would get 10.7 MHz. Very good. No matter which frequency, we can get it down to 10.7 MHz. This reduces the cost of our ADC already a lot. But still, to digitize our 150 kHz FM signal, we need a 11 MHz ADC. Not very efficient. We have to go further. What do we have to do to get the cheapest available ADC? We have to get the intermediate frequency to 0. What does this mean for our FM station? If we set the local oscillator to 100.7 MHz, we shift the center of our FM signal to 0 Hz. Now the ADC only has to handle up to 150 kHz, close to the capabilities of an Arduino. Very good. But wait, look at the diagram. Something is wrong here. We also get negative frequencies, and such frequencies do not exist in reality. In analog systems, they are cut off, and we lose 50% of our information. So this is probably not a good idea. This assumption lasted until a bright guy had an idea. He bent the negative part of the frequency axis by 90 degrees and added a small letter I. Some of you might recognize this chart. Instead of real frequencies, he invented complex frequencies. Guys who know these numbers know that we had to spend some time to learn to work with them, but they are useful in many respects. And fortunately, we have mathematicians who can do the heavy lifting for us. If they are done with their work, we can use ready-made software and do not have to bother about mathematical formulas if we do not want. However, if you want to bother and use your gray cells, I leave a link to tutorials made by Mike Ossmann about this stuff.
Hi, I'm Michael Ossmann of Great Scott Gadgets, and this is Software Defined Radio with HackRF, Lesson 1. Welcome!
It will take you at least 10 hours to complete, but it is fascinating. Essential for us is only. With this concept we can use the cheapest possible ADCs and do not lose any signal content. How can we bend this curve? Instead of a mixer, we use a so-called Quadrature Demodulator. It also has inputs for the radio signal and the local oscillator. And it has two outputs. One for the horizontal axis, in SDR speak called I signal, and one for the vertical axis called Q signal. Together, they form the famous IQ signal, similar to the MP3 signal for audio. The IQ signal is the standard for SDR. The only caveat is we need two ADCs instead of only one. This signal usually is transferred via USB to a PC where we have software which does the heavy lifting, like displaying the signals and demodulate it. By the way, do you know where this 100.7 MHz signal came from? No, it did not come from a commercial broadcaster. It came from this HackRF1, a transmit-capable SDR box. This is possible because what we learned before also applies to transmitters. If we use a quadrature modulator, we can generate whatever signal we want. But this is not all. What would happen if we used a faster ADC? We could sample more than the 150 kHz needed for one FM station. The whole FM band, for example, is 20 MHz wide. A 20 MHz ADC would be able to digitize all stations at once. Incredible! But is this possible? Yes, it is. The ADCs of this HackRF1, for example, are capable of generating an IQ signal of 20 MHz. And this $10 RTL SDR dongle still covers a few stations because it is capable of making IQ signals with 2 MHz bandwidth. Just that you understand right. If we record the 20 MHz IQ signal, we record all FM stations in our vicinity in one go. Perfect for organizations like the NSA or others interested in listening to secrets. You can imagine who were the first buyers of this technology and who still buys the fastest ADCs with the biggest bandwidth. As with MP3 signals, we not only can record, we also can replay any IQ signal. The only difference is that we use antennas instead of microphones and speakers. Maybe you understand now how these so-called replay attacks on older cars and other unsafe devices work. You hide behind a bush, record a signal of the original key, and replay it when the owner is gone. And because you can register a vast spectrum, you only have to know the frequency range of such a car key and use an ADC with some bandwidth. Cool stuff! Even cooler is that you do not need to know which modulation principle the sender uses. Like you do not need to know how Bruce Springsteen plays his guitar to listen to his music. You just hit record and play. You might think that replay is the coolest trick SDR can do, but there are much more essential usages. Until now, we only looked at the ADCs and therefore the bandwidth of the devices. Next, we have to look at the frequency range they can cope with. Most SDR devices cover a massive range from a few megahertz to a few gigahertz. So they include most available communication services like the ones shown here. If we go one step further, we have to ask ourselves, what happens with the IQ signal in the PC? Because it is digital, it can get a treat especial from the software. The most common software for SDR receivers look like this. Here you see all signals in a frequency range in a waterfall diagram. If you select the signal, you immediately hear sound. If we use a HAC RF1, we see the entire FM band with all stations. You see, I live in the countryside and we do not have a lot of stations around me. And you also see that I had to leave my lab, because I do not hear any FM stations down in the basement. At least I got some vitamin D like that. If we select the 2-meter amateur radio band, we can use the cheaper RTL SDR dongle, because the band is only 2 MHz wide and we would see every station immediately when it is calling. When I was in military service, I had the job to manually scan a frequency range of about 500 kHz and stop for all stations of other armies. With such an SDR receiver, one soldier could monitor a much wider band and would never miss a station. Who knows how the robot is called which has taken over my job? We also get very specialized software which works with SDR receivers. One example is RTL_433 used in video 209. Such software is optimized for a particular task like decoding and hacking signals of 433 MHz sensors. And if you use standard SDR receivers, these tools work without any problems. The king of the SDR software tools, however, is GNU Radio Companion. It is like the land of milk and honey. You can build nearly all sorts of transmitters and receivers you can imagine without touching a soldering iron. The only thing you need is an SDR receiver or transmitter and a PC. It even runs on a Raspberry Pi. This, for example, is my FM broadcast station. It takes a WAV file, creates a wideband FM modulated IQ signal on 100.7 MHz and sends it to the HAC RF1. The quadrature modulator of the HAC RF generates the RF signal and transmits it via this antenna. Done. And this is how FM receivers look like in GNU Radio Companion. It takes the IQ signal of the SDR receiver, demodulates it and sends it to the speaker. We easily can change the frequency to 145.525 MHz and the modulation from wideband FM to narrowband FM. Now we can listen to amateur radio. The same applies, of course, also for the transmitter. How cool is that? We can change the purpose of hardware solely by adapting the software. We saw now how software-defined radio works. Let's now have a look at the available hardware. I start with the cheapest ones, the RTL SDR dongles. These dongles can only receive and have a maximum bandwidth of around 2 MHz and a frequency range of 24 to 1766 MHz. You get several versions. The cheap standard ones are okay for playing around, and the more expensive ones like this RTL SDR version 3 come with some bells and whistles. The prices are in the $10 to $20 range. Incredibly affordable. By the way, do you know the story of these dongles? They were made to watch terrestrial TV stations and listen to digital radio. They are produced in high series for the consumer market and therefore are cheap. They were not intended to be used for SDR. Until two smart guys discovered how to switch on the debug mode. In debug mode, these dongles send the internal IQ signal via USB to the PC for analysis. And this is exactly what we need for SDR. Hacking at its best. The next is the HAC RF1. It was the first affordable SDR device and it can receive and transmit in half duplex, which means it only can transmit or receive at one point in time. It has a max bandwidth of 20 MHz and a frequency range of 1 to 6000 MHz. It uses 8-bit ADCs and its price is in the $200 to $300 range for the original or a clone. HackRF1 is supported by nearly all SDR software packages, and Michael Ossmann, its creator, is a great contributor to the SDR community. This is why I bought an original HackRF to help him, even if I get more competitive devices now. One of those designs is the Adalm Pluto. It is sold as an evaluation board. Its frequency range from 325 MHz to 3.8 GHz is not spectacular. It has a maximum bandwidth of 20 MHz, but it is full duplex and uses 12-bit ADCs, which means it is much more sensitive than the HackRF, which only has 8 bits. Because it is a newer product, the software support is not as good as with HackRF. Its price is around $100. Then comes SDR Play. They have several versions like the RSP2 Pro I have here. Its specialty is the 14-bit ADC, a frequency range of 1 kHz to 2 GHz, and excellent software which mainly runs with these devices. This makes it the darling for all amateur radio enthusiasts. It supports a maximum bandwidth of 10 MHz and its prices start at $100 and end at close to $300 for the duo containing 2 receivers. And yes, it is receiving only. The next is Lime SDR. With 61 MHz it has the biggest bandwidth of all and a frequency range of 100 kHz to 3.8 GHz. It uses 12-bit ADCs, can receive and transmit also in full duplex, and its price starts at $300. Up to recently, its software support was not comparable to a HackRF1 or an RTL SDR, so check before you buy one. The Lime SDR Mini is a compromise. For $160 you get 10 MHz to 3.5 GHz and half the bandwidth of 30 MHz. The other specs seem to be very similar to its bigger sister. Professionals prefer devices from Ethos. They start at $1,000 and maybe are not the first choice for hobbyists. And what about the software? As mentioned before, we get several categories of software for our SDR devices. The first category contains general-purpose receivers like SDR Sharp, SDR Console, HD SDR, GQRX, or SDR Uno. All of these packets create a so-called waterfall diagram for a specific frequency band and demodulate all sorts of signals, with a focus on audible signals like voice or music. Together with a cheap RTL SDR dongle, they are a perfect entry into SDR. The next category consists of software for a particular purpose. Often these packets are used for digital signals. Examples are the RTL_433 to listen to sensors, DAB player to listen to DAB radio, or RTL 1090 for receiving position information of all airplanes around you. The last category is software for analysis and testing. For example, RTL SDR Wide Spectrum Analyzer or RTL_Panorama. Both enable broad spectrum scanning like a spectrum analyzer. Or Universal Radio Hacker, which is a big helper for hacking digital signals. And of course, the IMSI catcher, if you are interested, who is using mobile phones around your house. GNU Radio deserves its own category as a universal platform to build wireless communication systems. It is also used in professional applications to test new communication protocols before they are implemented in mass-produced devices. I leave a link to a comprehensive list of SDR software in the description. If you are now interested in trying out this new technology, you find many installation guides for each software packet. Many run on Windows, but Linux still is the platform of choice, especially if you want to try special applications. Maybe you watch my video number 209, where you can also find a link to a Raspberry Pi SD image with some pre-installed tools. Like that you are up and running in a short time. Summarized, we learned that software-defined radios, similar to analog radios, use mixers to shift reception frequencies down to 0 Hz. They bend the negative axis by 90 degrees to not lose 50% of the signal content. Quadrature demodulators do that trick and create a universally usable IQ signal consisting of an I and a Q component. This signal then can be processed by software on our PCs or Raspberries. As an example, we built a universal transmitter and a universal receiver. And it worked on broadcast FM as well as on amateur radio. We looked at the various SDR devices available in the market and saw that you could start by spending less than $10. For $100 to $300 you get serious receivers, some even with transmit capabilities. We had a look at some specialized software packages which are useful for makers to hack or to receive signals. And I was able to mention the word complex numbers only once. Look at some other explanations of SDR if you want to assess how hard this is. As usual, I omitted 99% of all facts, but I hope I covered the critical 1%. And with the help of Google you can start or continue your own journey. Please write us in the comment where you already used SDR in your projects or where you see a useful application. On this channel, comments usually contain more information than the video itself. This video was not a cheap one. This is why I want to thank all my supporters on Patreon and viewers using my links for their purchases for supporting the channel. Without you, it would be difficult for me to do what I do now. Bye.